Daniele is going to talk about inferring parameters and states in your biological networks.
Thank you very much, Krasi, and everyone for organizing this very interesting meeting. It's a privilege to be here, and I want to talk a little bit about work that I'm doing across two universities or in collaboration with another university. I'm the Vrije Universiteit in Amsterdam, and we set up together with our sister university in Radboud a working group that is trying to bring methods and techniques from, I would say, PDE and the geosciences in the world of neurodynamics. So the main idea is that we have to, in some sense, not rediscover, but adapt in a very major way tools and techniques from uncertainty quantification and data assimilation and inverse problems, which is really the subject of the talk. We are very active on our channel on Zulik. This is a form of Slack. You are very welcome to contact us at any time. And I'll be talking mostly about the work that Khadija has done and Torben have done, and to a less extent of what Francesca has worked on. So I have actually changed every single slide since the meeting has started, mostly because I thought I had really completely mispitched them. But this one stayed. And I want to give you an idea for one way in which you could read or understand from which angle we are coming from. And so what you're seeing here is a simulation done on of a neural field model. But the model is not important. That's what I'm going to try and say. And it may, and it's the geometry is picked from the Human Connectome project. I shouldn't say synaptic, but the kernel is picked up from the Human Connectome as well. And you see there a mesh that is triangular. So you may be led to think that what we are doing is some form of finite element scheme along the lines of what people use for, I don't know, Navier-Stokes equation. And proving that this is the case is one of the themes of this group. So in fact, up to 3 years ago, there existed no scheme of finite element type that would guarantee convergence. I'm not saying there are no simulations that are showing, so we have there is plenty of even code that can give simulations of this type, but they're not really informed by convergence estimate, which is what we intend to do. So one thing that we want to do as a group is get out of the code and hope type thing in which our community sits, I think. What do we do with that, for instance, and this is part of the talk that it's part of the work that I will really not have much time to spend over, is to use these type of techniques to absolve one of the classical forward uncertainty quantification tasks. So uncertainty quantification is like a term that it's overused, that until I tell you what I really mean, it's kind of meaningless type. So in this situation, I brought this slide in because yesterday I've heard the word transcranial magnetic stimulation being put forward as some of the things that we could try and look into. So this is a forward UQ of a simulation of TMS. So the main idea is along the following lines. In TMS, we know that we stimulate prefrontal cortex of a patient, and the hope is that we stimulate somewhere in the prefrontal cortex and hope to reach, to elicit activity either in the limbic areas or in the back sort of areas of the cortex. And as you know, TMS doesn't quite work for everyone. It's very non-intrusive, but also it has the success rate that is not optimal. So for some patients it's good, for some other patients it's just like drinking water, let's say. So the way we like to cast this type of study would be the following. Somebody walks in with a model, and we are very agnostic about the model that we are considering, so I'll qualify this later. Somebody walks in with a model and walks in with a protocol for their TMS. So they're telling us how they intend to parameterize an external stimulus, for instance. And then, in this type of study, every element in the connectome has been perturbed with randomness. So as opposed to picking that as a parameter, we attach a distribution to each of the matrix of the connectome. And we attach a parameter distribution to each of the parameters that fall into the transcranial magnetic stimulation input. And the type of answers we would like to give is, on average, if you run like tons of experiment with tons of particle simulations, if you want, a certain point in the cortex is elicited with an activity that is above the 5% of its rest state, with a certain probability. So that is the type of computation that we want to enable with this type of work. And what I just told you, namely doing millions of particle simulations and fetching the results at the end, is almost a recipe for how not to succeed in doing that. Okay, so it turns out that you need to just be carefully doing discrete simulation, spatial discretization, as well as cleverly doing your realizations. But that is part of the talk I will not give you, because that's the one I canceled yesterday evening. So I will present very few theorems, in fact probably only one, but in general you can take this as being a model, or rather the model of a model. So we have been hearing already neural masses already quite a bit. Yesterday, this morning again in Vael's talk and in Mark's talk, there were like neural mass models. In here, I'm taking as a model of evolution a neural field. And the best way that I have to offer after you've heard this talk is think of a continuum equivalent of those models, in which the cortex is a continuum. I will not put any restriction on the cortex shape or its position or how complicated it is. For at least all the theory, that doesn't matter. And the constitutive elements are U, which is a measure of the activity at position X and at time T, the W, which is the connectome, nonlinearity F, which is a firing rate, G, which is an external stimulus, and V, that is the initial condition. And the reason why I will use this model, it's because when I'm wearing a numerical analyst hat, I want to have a model on which to benchmark my things against. When I have to prove theorems, that's what I have to do. But we employ these techniques in a wide variety of, I would say, generalizations of these models. So you can add, and you've already seen this happening in the past days, you can have multiple population models, you can have heterogeneities. This morning we saw an example in which the nonlinearity was happening here, for instance, and locally there was only just a term like minus omega happening there, but one can have generically nonlinear terms coming there. And you may have delays, which I'm not even putting here on the slides, okay? I'm not saying that everything will work. I'm saying there is nothing from stopping any of the schemes to work in these setups, and I've got theorems for the kind of neural field simple, let's say. So typically what we do in Arkham, these equations have a long history, and this is like a sub-list of people that worked on it. If your name is not on it, assume ignorance on my part. There is no malice at all. I just the list keeps growing, of course. And the classical way in which these gadgets have been used is to say, oh, one chooses synaptic kernel, one chooses a rate function as inputs to the systems, and out comes a voltage that we want to predict. And what we're doing, together with the people that I discussed later on, is on the one hand enable simulations that are provably accurate. So this is actually a point that I want to bring across. What really motivates us is to get schemes for which we can say, if you refine the mesh with these many elements in these many ways, then you're guaranteed to get closer to the truth by this much. And we want to put theorems attached to that, and then use them, of course. So this is one theme, but the other theme is the one that I will touch upon for most of the rest of the talk, which is the inverse problem. So to speak, have readings of the voltage and estimate some of the parameters or some of the states. And just, I think I'll skip these slides. I just want to give you a flavor in case you are a numerical analyst, and then maybe at least one person in the room that may care about this slide, of the type of techniques that we do employ that. So up until 2 or 3 years ago, there was no characterizations, as I said, of these schemes. So one of the things we did was to say, well, we want to build up the two big family of schemes that people use for PDEs, collocation schemes and Galerkin schemes done for these type of problems. So let's say we can call U the solution of the full problem in Banach space, so in full function space. U sub n is a discretization that we do with a projection either of the collocation type of Galerkin type, and we prove existence of the solutions, of the discrete solutions, and also error estimates for them. So this is the only kind of theorem slide that I will put in there, and just please bear with me. But it can give you a sort of idea for what type of work we're motivated by. So down here, there is the error that our scheme makes. U is the truth defined by the model, and as I said, we are kind of agnostic about the model. It can be bells and whistles on top of the neural field. UN is the discretized problem, and N is you can think of N as being the number of nodes or the number of modes of the discretization, and you're interested in sending this gadget to 0 fast across all space and time. And this is what this symbol tells you. And to the left and to the right, what we prove is that it turns out that if you want to estimate how fast this goes to 0, you have to look at how fast this other term goes to 0. And how fast this term goes to 0 is something that you can read from a numerical analysis book. So when people choose their meshes and their type of discretization, they are committing to a particular PN. And if we do our job correctly, we can then estimate these terms. So we know not only that as n grows, this term will go to 0, and therefore sandwiching the error will go to 0, but also how fast. And I'm going fast on this because I detect that this is really not perhaps something that you're mostly interested in, but I just want you to be aware that it's there. So we built up these 4 family of schemes: finite elements, spectral collocation, finite elements Galerkin, and spectral variants of them. And for each of them, we have predicted convergence rates of how fast they should go to 0 as n goes to infinity, and experimentally, where my experimentally now means numerically experimentally, finding those rates, and discovered also some new schemes that we didn't know they existed as we moved along. Which questions do you have before I move to a very different topic? No questions. Yes?
In the 2 previous ones, what about the lower bound, the theorem, the left side?
That's another, so I don't know what you see. I see a constant, and I see U minus Pn appearing on both the upper and the lower bound. So that one is so U is the true solution. Pn is one of the projectors that I've used. So this is either a collocation, sorry, I'm victim of my own slides. So Pn is the projector that is either an interpolation projector or an orthogonal projector. Do these terms mean anything? I'm just asking, am I helping? So Pn is a projector. So Pn times U is how the projector approximates a function. So in this case, if you decide to have an interpolation projector, you have an interpolation error. So you can estimate the term Pnv minus V is how well a function V, function of space, is interpolated, yeah, or how well a function of space is represented by including the first n modes of it, yeah. So this thing is under control if I know the, and this one is basically saying that the
Is m the same number, Daniele?
Sorry?
Yes,
there is m and 1 upon m. It's just a scalar that doesn't depend on n. It depends on, it's the same number, yeah? And so by controlling how fast I go, if I gain control over this sequence, I gain control on the scheme error. Am I helping or not?
But you always have an error, a positive error.
Yeah, there will be always.
You must have an error, yes, always. But that is true of any discretization scheme. The only thing you can do is push the error down up to a tolerance that the user tell me. So if you walk in and tells me I want to have the error up to 10 to the minus 13, using this theory, I can say you need 25 grid points. And if you want to get it better, I'll tell you use 40 points.
But you cannot get lucky.
Never, no. This is, unless your problem is trivial. No, you can't. Thanks. Okay, so now for something very different. One of the things we do is we're trying to employ these schemes on data assimilation problems. So for the next, hopefully 20 minutes, I will not discuss methods and schemes, but I want to give you a case study in how, that happened to us. Experimentalists came with a question. In fact, actually, we went out and searched for them, and they happened to have a research question. And I want to expose a little bit the cycle that we went through them to address this problem, using the schemes that we have come up with. So this is data that comes from Radboud, from the Battaglia lab. And I don't know if this is very visible to you, but what they do is they record slice of a mouse during sleep phases, and they are interested in understanding whether waves are formed within the cortex or they are influenced by the hippocampus underneath it. They record the cortex, so they give us LFP potential, local field potential, and they have long recordings, about 900 seconds of recordings, a very high temporal frequency, about 20 milliseconds recording in time, and these are all the pixels that they give us, okay? And as time progresses, I don't know if this is very visible over there, but you perhaps should concentrate on these two time slices. You should see a standing wave emerging. So you see black and yellow becomes black and yellow there. So you just have a motion of this type. And the type of question that they ask us is, we know that the hippocampus is there, we don't know what role it plays in these waves, and we don't measure it. We only measure the surface, so to speak. And when we get questions like that, we get very pleased because we think, okay, we believe we have a recipe, or we can start working with you on something. So Khadija, who is the PhD student who's working on this topic, started by developing a noisy version of the schemes I've just discussed. So Khadija decided to represent the neural field in this way. You will see this equation over and over again. You should read it as a neural field with the integral term simplified. Is an equation written in operator form. But you can equally well substitute these with your set of neural mass equations that you have thought about before. And there is some noise. For the time being, we're not making assumptions on the noise other than it can be additive or multiplicative. Later on, I'll commit to a specific noise type. And what Khadija does is they estimate the error that we make in the presence of noise in expectation. So they come up with error bounds, which are the lines that are written there, and then they also experiment that the scheme works for one noisy simulation of the neural field. So this time is now stochastic noise theory and a tailored scheme for that. So how do we use that? Well, we have a model now for a neural field that we have a neural field model or a neural mass model that is defined on the cortex. We attach some noise potentially to it. You've seen this happening already before. But the Battaglia lab is giving us some readings, some LFP readings.
So it's like a white noise?
So
I know at least
yes.
10 different noises.
So I think I have also 10 different answers to your question. Say, when I was talking about this thing here, yeah, this one was, I think in here notation is not helpful. There is if this means anything to you, there is a Q, there is a trace class operator nested in here. So it can be both white and colored, depending on how do I choose it over there, yeah? For the application, so the schemes don't sense that. They work in either way. But one has to be extremely careful to making sure that these ODE make sense in Banach in function spaces, yeah? For the calculations I will show in a second, you can safely think white noise. White in space, yeah, white in space. Thank you for the question. So as I was mentioning to you, the Battaglia lab come up with some LFP recording. So the right thing to represent, at least to me, is to say, well, they're giving us an average over a specific pixel that I call d sub I of the activity U that the model evolves. And in a classical data simulation cycle, the way this works is like that. We say we have a neural field, we have an external stimulation, which is how we are going to model the hippocampus influence. You will see that in a moment. I'll get to that in a second. There is noise that I still have to tell you exactly what it does, and you will see this more in a second. And then I have readings. This H operator is basically, it's basically a vectorized version of this operator that gives you the readings at all pixels there. And also this is affected by noise. And the idea is to approximate ut and theta, so to reconstruct states and parameter at once. And in this part of the talk, we are not trying to go sophisticated. We are taking an off-the-shelf particle filter that exists in literature. It's a nested particle filter, and I'm passing this message to you so as to say there are already questions we can attack with the schemes that we currently have. We don't need to just go more sophisticated than that. So how do we model the hippocampus? So visualize, this is meant to be a cortex in 3D, but yesterday I had too much whiskey, probably. And what you should visualize is a panel here that intersect at some point the cortex, and it leaves a trace like that. The reason why I'm doing this in 1D is because, as you will see in a second, it turns out that that's a good idea, but it's not obvious at this stage why. And I want to model the hippocampus there. So how do I model this hippocampus? I say there is an external forcing that is outside of the cortex, and I'm still not giving you a formula for it. I'm just telling you that there are 3 inferable parameters. These parameters are an amplitude, a wavelength, nu, and potentially a frequency of the hippocampus. And I am, in some sense, not stipulating anything else than a functional form for that. In the hippocampus, there is also a parameter, little a, that is Khadija's invention. And I want to keep it for later as to why this is important. They had a very good idea with that, and it has to do with the ground truth that was discussed later on. So the idea is that now we run the algorithm, and we are hoping to infer parameter theta and state u. The way we do it, and now I'm telling you which noise I'm picking. From here you can see that it's completely white. I'm discretizing space, so now also time is continuous, and you have discrete time readings, as you do, and discrete temporal reading for u. And for simplicity, we pick up this sigma u and sigma y as being just 2 parameters. So I have basically a matrix, an identity matrix in front of the noise. So this is completely white noise. And one thing that I don't see much said, so I think I should stress it here, is that these two, because the model I picked here is deterministic, I could also pick a stochastic model to start with. But in here I'm picking a deterministic model. These 2 parameters, they help you deciding whether you put your trust more in the data or into the model. So if you set sigma u large, you are mistrusting the model with respect to your data, and vice versa. So these are things that you can tune. You can repeat the analysis in this way. Okay. The first thing Khadija did is testing with synthetic data. And when you have synthetic data, you have a ground truth.
Just before you move on, so
Of course.
basically you're saying that they complement each other. Is that what you're saying? That are they independent of each other, these 2 noise terms?
That depends on what you pick. So if you make sigma y to be
So one of them is
1 minus, if you do 1 minus sigma u, which you can pick, you really have a slider.
Slide, okay.
Yeah? But in general, you can also vary them independently with respect to the noise intensity. So the first thing Khadija did was testing with synthetic data. So this is a situation in which you establish initially your parameters. So you pick your parameters. You run the simulation of the model. You use that simulation to make you give the y. Okay?
That's the ground truth.
That's the ground truth, but there is a twist on that. And then you now blindly ask your algorithm to rediscover the parameters that you picked. Okay? Now, when we discussed this with Khadija, they had the intuition that this was too lenient to do. So what did they do? They said, well, I want to add an extra parameter, a, that is not inferable, that I will use only for generating y and not for inferring the parameters. Why do they want to do that? That's a great idea. It says, when you're given data, you will come up with an imperfect model. So what Khadija wants to do is create a situation whereby the data is generated by a model, and the model that we use for inference is only part of it. And this manifests itself through this little parameter a. So the data generated by Khadija has a frequency that accelerates over time. But the filter assumes that this frequency is constant. We want to mimic epistemic uncertainty, the uncertainty in our model when we do that. Yes?
Can I ask a quick question?
Of course.
So you have this L in front of UK?
Yes, it's linear.
Ah.
Yes, so I'm making it, I'm just, in this case, because the readings that we get there are integrals, they happen to be linear function of u. Must they be linear? Not for the analysis, but for the computation that we did, yes.
Why do you have quadratic dependence on time?
Where is it?
AT times T.
Yes, very good question. So imagine A was 0, then you would interpret F as a frequency.
Yes.
Yeah? And Khadija wants to have a situation in which the frequency is time dependent and it accelerates with time.
Oh, that's why. But
Just
then-
artificially, yeah?
But it will because it multiplies T anyway.
No. If I set F constant
Okay,
and I
okay,
only
I
have
see,
F times T, that's a constant. So Khadija wants to have a decelerating in fact A. But only the data know it, the model doesn't know it. Yeah. Thanks for the question, Krasi. Okay, so they now set up a synthetic data. That's the data set that has been generated, and that's the reconstructed estimate. And at 1 pixel, space is horizontal, time is vertical, and as 1 pixel goes over time, you know, the job is doing pretty well, at least in the eyeball norm.
How big is A?
You'll see it in the next slide. I still have to tell you that. But what I want to do here is I have a message for Mark, if he's in the room. No, he's not in the room, but at some point, Mark, at some point today, pointed out the difficulty that we have to do this type of study when we step over a bifurcation, when you have these nonlinearities, yeah? And I think this type of filtering, which do precisely that, we are stepping over a bifurcation there, they can help you with that. They can help with that situation too. So in this case, A is of order 1. So you see that after a burning period of 20 seconds, this is not 20 computational seconds, this is 20 time units of the experiment seconds, we reconstruct the parameter, A is there, the spatial wavelength is there, and the frequency, it's the red is truth and blue curve is the reconstruction. The frequency is not a parameter, which is good news. Yeah, first off, I didn't try to get it didn't detect that F was constant. But also, in a world where you don't know the red curves because you don't have the ground truth, you can still make sense of these two as being parameters and perhaps look at these data and say, oh, I shouldn't interpret F as a parameter. I should interpret it as a variable. And in fact, you can also get some information about how the slope goes, right? So if you were not given the reds and you're seeing just the blues, you could still do something even if the parameter is not inferred properly, which is, I think, fantastic news for us. And in my opinion, this is what we should use to go past bifurcations.
So, out of curiosity, have you tried time dependency on other parameters as well to see if that actually...
No. But you see now one very messy recording of real data in which we're trying to do that. So we're now in a situation where Khadija has the time stepper appropriately. They have a scheme that seems to be inverting parameters correctly, and it's time to bring in real data. And the first thing they did, which is wise, is to look at the data and try to understand what data they have to look at. And the first thing they do is to test space and frequency at every location here. And what they find is that the data set that they're given has only a very mild dependence on position. So if you pick up a pixel in the top left or a pixel in the bottom right, more or less the frequency peaks are more or less there. Okay, so the frequency depends, I mean, the spectrum density is different, yeah, I'll give you that, but more or less the kind of frequency peaks are there. And then what they did is they started sectioning the cortex with fixed space and x constant and y constant across time. So these are very long recordings. The mouse is known to undergo some different sleep phases, from sleep-wake SWS to REM phases, and these are all like one after the other in time, so to speak. And you're seeing a section horizontally and a section vertically. And when Khadija presented me these, I said, oh, that's not very useful. What I see is that there are all sorts of wavelengths. We have to go and read what wavelengths we have. But Khadija, being the sleuth that they are, they told me, look again, there is a lot of information there. It turns out that for reasons that we didn't see, all these data had zero activity at the boundary. And this is completely odd. Why should we expect that? Quick phone call to the Rabout, and they tell us, oh yeah, we put there an artifact. Because what we know is that we are doing the recording thinking that the cortex is a plane, but there will be problems on, tapering problems that come from the optical reading that we do. So we do mistrust the reading there. And that's why we basically have some sort of bell curve that helps us setting that close to 0. Which is actually more good news. It's good news that Khadija picked it up. I would have never picked it up. But this is also information that you use in the process. Where do you use it? So earlier on, we were asked about L, remember? And now I can make L have that information there. So Khadija then injected that L, the information that at the boundary you should get 0, because that's compatible with the data set that we get. No cheating, it's just proper information there. And then Khadija did the thing I wanted, namely, we told them to do, which namely was to try and look at the wavelengths that are associated with it. So now, in this situation, we pick a slice, a horizontal slice, and then for each times, at each time, you have a function of space, you compute the wavelengths associated with them, you bin them, you aggregate them over time, because we want to understand what sort of wavelengths are seen in the data. And what they find is that effectively, whether you go vertically or horizontally, there seem to be dominating large wavelengths that persist, and small wavelengths are really rare. So the type of signal seems to be able to be described with very large dominating wavelengths as we move on. I'm almost there with the data. And that's the last slide I have for data analysis. So another thing that we could do at this stage was to go and do the particle filter directly in 2D. Because ultimately we have a neural field, we can do it in 2D, and the particle filter would just simulate these large 2D cortices. But again, the idea here was to try and understand what type of phenomenon we're looking at. Are we really looking at a 1D phenomenon, or are we looking at a 2D phenomenon? Because if I look at the slices that I just presented to you, it seems that there is not an enormous difference about that. And Khadija went and picked up a trick that is in use in imaging, that is the radon transform. So what a radon transform does, it lets you transfer your 2D data onto a 1D line whose angle you choose a priori. So one way in which you can try and do a 1D version of your 2D data is to say, pick a center, pick an angle, and then the radon transform would just basically accumulate your signals and bring it on that line, so that you can then eventually vary the alpha and try to redo your analysis. And what Khadija finds out is that the wavelength of the wavelength I've just discussed, as well as the frequencies, the temporal frequencies that I've just discussed in the data, it's not terribly dependent on alpha either. So that prompts us to say it's not completely out of the blue to do this in 1D. Or at least we could try and do this in 1D. And on they go, and they do it in 1D, and now this is real data in red versus the reconstruction that we have in black. And these are 4 pixels that I've selected, and they seem to be going all right. Actually, they have they follow the signal rather well, let's say. And when it comes to parameters, this time the parameters are not as clean as they were before, but the data is also real data. We're gonna get, and I think that's probably the only answer I'll give you about the biological significance of what we found, because that's Khadija's paper 2, and Khadija's paper 1 has been submitted yesterday. So I will only talk to you about the methodology of it for now, is the model that we have and the forcing that we have is compatible with effectively the hippocampus impinging with an amplitude that is non-zero, with a wavelength that is non-zero, and with temporal frequency that oscillates mildly around 0. One of the things that happen here is that because the type of filtering we're doing can also follow, as I said, it doesn't try to be constant in time if the data doesn't let it be constant in time, we sometimes see things that are relevant. So in here, I think I've been very vague about the coloring, gray, green, red, and that was intended. It's because until this point, we didn't discover that these colors were there. So the way this happened, it was once again, we just went to the people in Radboud and asked them, this is genuinely not staged, yeah? We said, look, we see a blip at around 400. And we don't know if it's physiological or if it's just the algorithm that is giving us something like that. And they said, oh, we know what happens. You know, the mouse has entered SWS phase. They had basically labeled the recording with the phases, it's just we didn't have the data sets. Okay? So this is the type of things that this type of analysis can do, and I hope I've convinced you a little bit that it is...
So is it actually like a tipping point then used to
what I think the conclusion I have, but this is the conclusion I have as of yesterday, is that at some point it feels like the hippocampus is giving it a big kick
But isn't it
prior
changing?
to SWS.
Predicting that the next phase is coming up.
Yes, but you see, I'm just I'm trying to be cautious about the whole process, but that's compatible with what you say. Kazi, you had a question.
Well, that's the same. It was the same.
Yeah.
Same square.
It feels like it's receiving a kick
that's-
before going to sleep. But somehow, but let's say I also have to be cautious not to overpromise. Yeah, the reason for it is that I believe that they put a green label before we did the analysis, so they must have seen this without our algorithm. You see what I mean? I think this must not be news for people in Radboud if they flag this as green.
But when it is a different state for the mouse, isn't it?
Yeah, it's a different. Yes.
So they would know that, yeah.
Yeah, exactly. So it's just that we didn't know the labeling, and it was happy for me to find out that this was not a blip in the system. One of the things that the filter does, it does bad at high frequencies. It's called a filter for a reason, yeah? And so what you're seeing here is what happens to the signal when you take the PSD across the entire cortex and across the entire time for one point in the cortex. And as you see, the algorithm does a very good job, and I don't understand why it does a good job. This is a very large dimensional inversion. Yeah, I have about hundreds of spatial points and the 4 parameters for them. So this is actually, it's not for granted that this should work this well, but it seems to be working all right, surprisingly well, in fact, at picking up frequencies also in the very high band. And of course, because we don't try to do code and hope, we also try to quantify a little bit what is the root mean square error that we do across time, and also what is the frequency shift that the algorithm does across different angles. Remember that all my data set is angle based, and this seems to be working all right across all angles. So, as I said, I hope I have convinced you that we have not solved the problem, but this is a very useful dialogue to have with an experimentalist. And it's a mix of modeling and data exactly of the type that I like. So not doing data analysis without a model and just refining. I think this is really the right place to be, in my opinion. Or at least that's something that excites me, let's say, and I hope it excites you too. I think I have 5 minutes, can I have? 4?
Yes.
Yeah?
Because we started 5 minutes later.
Yeah, so I think I'll take even less than that. So the impression, so as I said, I decided to present you Khadija's work to give you an impression of what can already be done taking off-the-shelf schemes. But there is a very buzzing community in the mathematical statistical front, and the people that are working with us on this are part of that community that are really trying to develop new filters for large dimensional problems. So I was really lucky enough to just move next door to Frank van der Molen, who is effectively an expert in doing this type of inversion, and he has ideas for how to make better filtering. So I want to spend the last 4 minutes of this talk going back a little bit more to the theoretical part of it. So what Frank, and I think it's actually Torben is doing this work, the PhD student that works with us, and Frank, they look at this problem on generic Hilbert spaces. So they are thinking of an SDE that works on an infinite dimensional dynamical system, and this is where I have to be super careful about the noise that I pick there. If I'm trying to solve the problem in function spaces, taking taking white noise actually for neural fields, unlike PDEs, would lead to nonsense. So white noise is not well defined for neural fields for integral differential equation. It has to be color noise. So this is why, we have the trace class operator very well visible over there. They tell me, well, you give us this observation operator that is exactly the one we have used in Khadija's work, and they are right in the framework that we want, and they want to study it theoretically. So what's the right framework for that? And this may not be news if you've done data assimilation before, but I still want to discuss it there. So in here, you have a sample of the stochastic process that undergoes these SDEs, and that's one sample of it. Having observations, what I call Y, from a probabilistic viewpoint means having observations, having realizations of a random condition variable. So when you establish that Y and U are related in this way, since U is a stochastic process, what you get out is Y conditioned on U. Which is why the idea is just that each of these observations that come available to you are members of a condition process and are samples of a condition process. And the data assimilation task is the task of effectively predicting UTI, well, having an estimate of the probability of UTI given all the past readings that you have. There is also the smoothing, but I'm not going to get into that because I have no time. So what's the idea that Frank and Torben have? It's based on a variation of a Dupes transform, which is also a tool that has been around for quite some time. So what does the Dupes transform does in pictures? It says like that. This is the process your model, let's say, that is stochastic. And that's clearly not what you have to simulate, because at some point, well, first off, you have a cloud of them, yeah? But also that's what you would simulate if you didn't observe anything. Now, all of a sudden, at a future time t, comes an observation y. So you now get one instance of y given u. And you wish to sample u given y. Of course, they use Bayesian, these are Bayesian probabilists at work. And what Dupes transform does, it comes up with a different process. So this one is now a modified SDE with an additional term here. And the purpose of Dupes transform is to push, to tilt the dynamics towards the observation and the future time. This is a very, very cute gadget. The idea is that one has to come up with there is an algorithm for computing h, and once you have h, you can tilt the dynamics in that way. So now, to cut a long story short, how do you define big H? You need a function little h that has to do with the probability, the density of y given u, as well as the probability transitions of the Markov kernels associated with u. Sorry, the Markov kernel associated with u. And if you know h, then big H is just a matter of taking the derivative of its logarithm, and I'm not getting into the detail of that. What I'll get you in the details of is that big H hinges on knowing little h. And the reason why we cannot use this approach is because little h is not computable. Because to define it, you need this kernel, and this kernel means basically you have to own this SDE. So that's typically tough. But Torben and Frank have a fix for that. They say, rather than taking the condition process, let me come up with a G that approximates H and that it's computable. And in that case, I have like an algorithm that it's doing that. And the way they define that, but I think I'm going too fast to make justice to their work at this stage, is they say H was not computable before because I had in here the transition process for U. Let me take the transition process of an Ornstein-Uhlenbeck process of which we know everything, and in particular we know nu, and therefore this G becomes computable. And to cut a very long story short, those two were Frank and Torben that you've seen going, is that we test this kind of filtering on synthetic data this time, on a 1D neural field model that has got a Turing bifurcation or a traveling wave bifurcation. And I like this slide, because Torben made me think for the first time when they did it, that this slide, it makes you really internalize what it means to be a filter. What it means to be a filter is that you don't see this. You only see these dotted observations, and your job is to reconstruct that stuff that is on the right and on the left-hand side. And that's precisely what the guided filtering does by just constraining the activity at each, well, the samples at each of these readings as they become available. And what Torben does, and I'm closing now, it compares it with plain vanilla filtering, and scented Kalman filter is the right thing to compare against, because by using an Ornstein-Uhlenbeck process, we are doing a sort of linearization of the system, and therefore the unscented Kalman filter seems the right thing to do. And listen to this, we get the same performance as the unscented Kalman filter, which seems disappointing at this stage, because the error that we make is basically the same as an off-the-shelf tool. So why do we do that, and why am I talking to you about that?
Exactly. That was my question. Sorry.
Because if you're not careful, you produce garbage with UKF. Let me show you how. So at the moment, you have, we have taken these observations. Remember, I had this grid of observations, and I think we did 20 of them. Okay? Now, what we do in the experiment on the left-hand side is we take the unscented Kalman filter, and then we omit some readings, assuming what happens when you have like a large scarcity, you have more scarcity of your data. And because the unscented Kalman filter does a linearization, you should expect it to do very bad when your epochs of observations are large. And there you see it with an error blowing up in time. So this is what happens to your reconstruction as time progresses. Whereas what happens on the right-hand side with the idea that Torben has is that because your dynamics is constrained to go back to when the reading is, it manages to keep that error constant, which is actually remarkable. And Torben has worked, we don't have an error proofs for that, but Torben has really worked on making this solid on function spaces, which is a very non-trivial task. So I'll leave you with a few references, and thank you very much for your attention. I'm at -8, I don't know.
I know, but maybe 2 minutes for very quick questions. Questions? I have one question.
I have a quick question about the last page.
The last?
Equations that you were showing, it really reminds me of kernel embedding. If you go back.
You mean these type of things?
Yes, yes, here.
Yeah.
And will it depend, this h of tu, depend on the form of your kernel that you will be using? That
By kernel, you mean now kernel? Sorry?
The k function and such.
Yes, so there are two. Can I just try to? First off, I do not know kernel embedding, but I can tell you where the kernels are.
Yeah.
So the word kernel for me in this thing is used here because that's the Markov kernel of transition probability. And what this thing here, I know that the letter K seems like kernel, yeah? But this is really the probability density of observation given you.
Okay.
So if you call that a kernel, then that's, but I think you may be referring, I don't know what kernel embedding you have in mind, but that's the kernel that I think more in your field people will call a kernel. You see what I mean?
Thank you.
And if this reminds you of anything, then there is every chance that there are connections. It's just that I'm not equipped to discuss them, and you are better placed for doing that. So we should chat later. But I really think that this must be downright your path, because effectively what this thing is doing is trying to condition the state of the system to a future reading. Irrespective of the, I mean, it's with the model, if you call this U, or even model less if you have this Ornstein-Uhlenbeck process attached. So I think there need to be connections.
Yeah, there will be.
Yeah.
Because it looked also from the graphs that you
That we
showed
get.
earlier where, the uncertainty and then go.
And then you just
And
push
forcing
them
it
down
Yeah,
there.
yeah. It's very interesting. Yeah.
Sorry, I know you want to. Just coming from the other way around. So you started with a pattern on the cortex, and you tried to explain what hippocampal input might have shaped or
Yes.
modulated this.
Yes.
Yeah? Can you think about it in the other way around? That you want a particular pattern on the cortex. What do you need to inject at the hippocampus to achieve it?
So what I hear you're going for, but you should correct me if I'm wrong, is more of a control situation in which you have a target control.
Yes.
So the last scheme I discussed is effectively a stochastic control term, yeah, and there are similarities and intersections even between data assimilation problems and control problems. But typically the kind of control thing, it's another field. It's something different. It's not that I'm not interested in. Actually, I'm very interested in it, but I've not yet explored it. Yeah. So this was more offered as an inverse problem type in which I'm trying to get the state and the parameters. Yeah. But I completely agree that.
Yeah, you can design, you can think about your desired controls and then find the parameters for that kind of thing.
Yeah, and put some constraints as well. You can just say, as I move, I also constrain some dynamics within, not even with a ball, but some state variables have to be kept within certain regions. Yeah.
Okay, let's thank Daniele again.